Good morning, children. Today we are going to start a new lesson from Science and Technology, Part 1, Lesson number 1, Gravitation. So let's begin. First, introduction. Can you recall, children? What are the effects of a force acting on an object? A force can be set a body in motion. For example, a steady car gets motion on pushing it. A force can stop a moving body. For example, a moving car can be brought to rest by application of brakes. A force acting on a body can change the speed of the body. For example, when brakes are applied to a moving car, its speed decreases. A force can change the direction of motion of the body. For example, a volleyball player applies force to change the direction of ball. A force can change the speed as well as the direction of the motion of the body. For example, when a ball bowled by a bowler is hit by a batsman, there occurs a change in the speed as well as the direction of motion of the ball. A force can change the shape and size of the body on which it acts. For example, when a spherical clay ball is pressed, it gets deformed and hence no longer remains spherical. Also, there can be a decrease in its volume. What types of forces are you familiar with? Yes, gravitational force, nuclear force, and electromagnetic force. Right? So, what do you know about the gravitational force? Yes, the gravitational force is a universal force. That is, it acts between any two objects in the universe. We have seen in our previous standard that the gravitational force is a universal force and it acts not only between two objects on the earth but also between any two objects in the universe. Let us now learn how this force was discovered. Gravitation. As we have learnt, the phenomena of gravitation was discovered by Sir Isaac Newton. As the story goes, he discovered the force by seeing an apple fall from a tree on the ground. He wondered why all apples fall vertically downward and not at an angle to the vertical. Why do they not fly off in the horizontal direction? After much thought, he came to the conclusion that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. The direction from the apple on the tree to the center of the earth is the vertical direction at the position of the apple, and thus the apple falls vertically downwards. Shows an apple tree on the earth. The force on an apple on the tree is towards the center of the earth. That is, along the perpendicular from the position of the apple to the surface of the earth. The figure also shows the gravitational force between the earth and the moon. The distances in the figure are not according to the scale. Newton thought that if the force of gravitation acts on apples on the tree at different heights from the surface of the earth, can it also act on objects at even greater heights, much farther away from the earth? Like, for example, the moon. Can it act on even farther objects like other planets and the sun? Now children, we learn force and motion. We have seen that a force is necessary to change the speed as well as the direction of motion of an object. Can you recall, children? What are Newton's law of motion? The Newton's law of motion are as follows. First, Newton's first law of motion. An object continues to remain at rest or in the state of uniform motion along a straight line unless an external unbalanced force acts on it. Newton's second law of motion. The rate of change of momentum is proportional to the applied force, and the change of momentum occurs in the direction of the force. Newton's third law of motion. Every action force has an equal and opposite reaction force which acts simultaneously. Now children, we will learn Kepler's law. Planetary motion had been observed by astronomers since ancient time. Before Galileo, all observation of the planet's position were made with the naked eyes. By the 16th century, a lot of data were available about planetary positions and motions. Johannes Kepler studied these data. He noticed that the motions of planet follows certain laws. He stated 3 laws describing planetary motions. Let's see the 3 laws of Kepler's. Kepler's first law. The orbit of a planet is an ellipse with the sun at one of the foci. The elliptical orbit of a planet revolving around the sun. The position of the sun is indicated by S. Kepler's second law. The line joining the planet and the sun sweeps equal areas in equal intervals of time. AB and CD are distances covered by the planet in equal time. That is, after equal intervals of time, the position of the planet starting from A and C are shown by B and D respectively. The straight line AS and CS sweep equal areas in equal interval of time. That is, area ASB and CSD are equal. Kepler's third law. The square of its period of revolution around the Sun is directly proportional to the cube of the mean distance of a planet from the Sun. Thus, if r is the average distance of the planet from the Sun and t is its period of revolution, then t square is directly proportional to r cube. That is, t square upon r cube is equals to constant equals to k. Let this be equation 1. Kepler obtained these laws simply from the study of the position of planets obtained by regular observations. He had no explanation as to why planets obey these laws. We will see how these laws helped Newton in the formulation of his theory of gravitation. So, Newton's universal law of gravitation. All the above consideration, including Kepler's law, led Newton to formulate his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and inversely proportional to the square of their distance between them. This figure shows two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies can be written as F is directly proportional to m1 m2 upon d square, or F is equal to g m1 m2 upon d square. Let this be equation 2. Here g is the constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. In case when bodies are not spherical or have irregular shape, then the direction of force is along the line joining their centers, and d is taken to be the distance between the two centers of mass. From equation 2, it can be seen that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in SI units, the value of g is equal to the gravitational force between two masses of 1 kg kept 1 meter apart. The center of mass of an object is the point inside or outside the object, at which the total mass of the object can be assumed to be concentrated. The center of mass of a spherical object having uniform density is at its geometrical center. The center of mass of any object having uniform density is at its centroid. Why did Newton assume inverse square dependence on the distance in his law of gravitation? He was helped by Kepler's third law in this as shown. Now let's see some solved example. Example 1. Mahendra and Virat are sitting at a distance of 1 meter from each other. Their masses are 75 kg and 80 kg respectively. What is the gravitational force between them? So, given R equals to 1m, m1 is 75 kg, m2 80 kg and g is 6.67 into 10 raised to minus 11 nm square per kg square. F is equal to G m1 m2 upon r square. So F is equal to 6.67 into 10 raised to minus 11 into 75 into 80 the whole divided by 1 square n. So the answer comes 4.002 into 10 raised to minus 7 n. The gravitational force between is very small force. It is 4.002 into 10 raised to minus 7 n. If the force of friction between Mahendra and the bench on which he is sitting is 0, then he will start moving towards Virat under the action of this force. We can calculate his acceleration and velocity by using Newton's law of motion. Now, second example. In the previous example, assuming that the bench on which Mahendra is sitting is frictionless, starting with 0 velocity, what will be Mahendra's velocity of motion towards Virat after 1 second? Will this velocity change with time and how? Let's see the solution for this. Given force on Mahendra is equal to F is equal to 4.002 into 10 raised to minus 7 n and Mahendra's mass, that is m, is 75 kg. According to Newton's second law, the acceleration produced by the force on Mahendra, that is m, is 75 kg. So, A is equal to F upon m, that is 4.002 into 10 raised to minus 7 upon 75. After calculation, the answer is 5.34 into 10 raised to minus 9 meter per second square. Using Newton's first equation, we can calculate Mahendra's velocity after 1 second. Newton's first equation of motion is V equals to U plus AT. As Mahendra is sitting on the bench, his initial velocity is 0. That is U equals to 0. Assuming the bench to be frictionless, V is equal to 0 plus 5.34 into 10 raised to minus 9 into 1 meter per second. So we get 5.34 into 10 raised to 10 raised to minus 9 meter per second. Mahendra's velocity after 1 second will be 5.34 into 10 raised to minus 9 meter per second. This is an extremely small velocity. The velocity will increase with the time because of the acceleration. The acceleration will also not remain constant because as Mahendra moves towards Virat, the distance between them will decrease, causing an increase in the gravitational force, thereby increasing the acceleration as per Newton's second law of motion. Now let's study Earth's gravitational force. Will the velocity of a stone thrown vertically upwards remain constant, or will it change with the time? How will it change? Why doesn't the stone move upward all the time? Why does it fall down after reaching a certain height? What does its maximum height depend on? The earth attracts every object near it towards itself because of gravitational force, right? The center of the mass of the earth is situated at its center. So, the gravitational force on any object due to the earth is always directed towards the center of the earth. Because of this, an object falls vertically downwards on the earth. Similarly, when we throw a stone vertically upwards, this force tries to pull it down and reduces its velocity. Due to this constant downward pull, the velocity becomes zero after a while. The pull continues to be exerted and the stone starts moving vertically downward towards the center of the earth under its influence. Let's see some solved example, children. Example 1. Calculate the gravitational force due to the earth on Mahendra in the earlier example. Solution. Given mass of earth, that is m1, is 6 into 10 raised to 24 kg. Radius of the earth, that is r, is 6.4 into 10 raised to 6 meter. Mahendra's mass, that is m2, is 75 kg. G is equal to 6.67 into 10 raised to minus 11 nm square per kg square. Using the force law, the gravitational force on Mahendra due to earth is given by: this force is 1.83 into 10 raised to 9 times larger than the gravitational force between Mahendra and Virat. F is equal to G m1 m2 upon r square. F is equal to 6.67 into 10 raised to minus 11 into 75 into 6 into 10 raised to 24 the whole upon 6.4 into 10 raised to 6 the whole square n, which is equal to 733 n. Example number 2. Starting from rest, what will be Mahendra's velocity after 1 second if he is falling down due to the gravitational force on the earth? Let's see the solution. Given u is equal to 0, f is equal to 733 n. Mahendra's mass, that is m, is 75 kg. Time t is 1 second. Mahendra's acceleration a is equal to f upon m, that is 733 upon 75 meter per second square. According to Newton's first equation of motion, v is equal to u plus at. Mahendra's velocity after 1 second is v is equal to 0 plus 9.77 into 1 meter per second. V is equal to 9.77 meter per second. This is 1.83 into 10 raised to 9 times Mahendra's velocity in example 2 on page number 6. So children, use your brain power. According to Newton's law of gravitation, every object attracts every other object. Thus, if the earth attracts an apple towards itself, the apple also attracts the earth towards itself with the same force. Why, then, does the apple fall towards the earth, but the earth does not move towards the apple? The earth and the apple move towards each other, but the magnitude of the displacement of the earth is negligible relative to that of the apple. Therefore, the earth does not move towards an apple. The gravitational force due to the earth also acts on the moon, because of which it revolves around the earth. Similar situation exists for the artificial satellite orbiting the earth. The moon and the artificial satellite orbits the earth. The earth attracts them towards itself, but unlike falling apple, they do not fall on the earth. Why? This is because of the velocity of the moon and the satellite along their orbits. If this velocity was not there, they would have fallen on the earth.